very glad that I'm talking after Tal and Jonathan that provided an excellent explanation about what quantum computers are, because I'm not a physicist. What I want to talk about is really how quantum computers are used for different applications. When do we expect this to happen? So on the right-hand side, you see a water, molecule of water. I think everyone remembers from our chemistry lessons in mid-school that water are 3 atoms, H2O. On the right-hand side, we have penicillin. Penicillin is a 41 atom molecule, highly used, right? The state of the universe today, the state of compute today, is that we are able to simulate at a subatom level only very, very few molecules. We can simulate water, but we cannot simulate penicillin. When I'm talking about simulation, I'm talking about all the different interactions that this molecule can have with other molecules, all the different states where the electrons can be placed on the different orbitals. This is something that is beyond the ability, because it's the combinatorial complexity is so high, it is beyond the ability of us to simulate. And it would take us 10 to the 86, more than the atoms in all the universe, as Jonathan just said, just to be able to do all this modeling of what a penicillin is. And actually, in a few years, when we're going to have 286 qubits, we might be able, finally, to model what penicillin is. So this is just to get us to the point. And so what are quantum computers good for? What are the different domains where a quantum computer could really help us? Definitely, it's not big data. It's something else. So we talked about modeling. And modeling, we talked about a 41 atom molecule. It's not a very, very large molecule, but the combinations are very, very large. So any type of problem that you have where the number of combinations, where the modeling, where simulating it becomes exploding, we're not able to do today. Another very large domain of mathematical problems are problems of optimization. When we need to optimize many, many different options. And usually the classical problem that everyone brings is the traveling salesperson. It's a very simple problem. We have 50 cities, and we have a salesperson that need to visit each one of the cities once. What is the best way for him to travel that will optimize and shorten the route? YouTube. Exactly. So if he does need to travel and he can't use the YouTube, this or Zoom, it will cause, it's exploding. All the different possibilities of going through these different 50 cities is something that we are not able to simulate in a lifetime. Another area that we're talking, Jonathan also mentioned, and Tal, is machine learning. Today, we are using very, very strong computers to do the training and the machine learning, but usually we assume that the data is pretty much valid. What happens if we want to do machine learning with a lot of uncertainties? What happens if we want to train tons of data in the future? How can we accelerate it? And another domain of mathematical problems are cryptography problems. Quantum cryptography, Jonathan mentioned RSA here. So we need to understand that today we're in the days of, let's say, the calculator. Everyone had a Casio calculator once. And we're now starting to see all the paths that will take us to what we have today as a computer from the calculator days. And what will enable this is actually being able to develop an ecosystem. For example, if you think about graphic processors, GPUs, so 15, 20 years ago when we started to have GPUs, they were used for graphics. They were used to actually send polygons to the screen. But we developed a lot of frameworks, we developed languages, we developed algorithms, CUDA, TensorFlow, Caffe, all these different frameworks enable us today to use graphical processors, GPUs, to do machine learning, to do optimization problems, and to do many, many different tasks. Similar, we need to do with quantum computers. And one more thing, if we're thinking about the world, our physical world around us is actually based on quantum mechanics, as we just heard. So really the native operating system to solve real physical problems is by using quantum algorithms, quantum computing. And the applications that we're going to talk now about are applications that are actually native to the way the physical world is operating. So I'm going to use a framework that is used by Boston Consulting, and I think it gives a very good idea of which verticals, which types of applications are going to be accelerated with quantum computers when this will happen. On the x-axis, you can see shorter to longer time frames. Problems that can be solved with maybe hundreds of qubits, and problems that would need very high quality, thousands and tens of thousands of qubits or more. On the y-axis, you can see problems that have huge impact, huge value in the verticals that they are, versus problems that have a good impact, but maybe a lower one. And you can see the racers, the racing teams. They're the ones on the right upper square. And of course, quantum chemistry is maybe the racing horse of the industry, because already with tens and hundreds of qubits, we will be able to simulate for the first time at the subatom level these molecules. We will be able to simulate this penicillin molecule and other molecules. This has huge impact on materials for batteries, for displays, for planes, for many, many different things. So quantum chemistry is definitely a racing horse. On the left upper side, we see the followers. We see again industries with huge value of being able to use quantum computers, but this type of applications need thousands and tens of thousands and even more qubits, and are maybe much, much longer, more than a decade away. And here we're talking about, for example, pharma, both drug discovery, the ability to design new drugs, as well as clinical trials of drugs, the ability to simulate and understand how these drugs are going to have side effects or not on many different types of populations. It's much, much growing larger numbers than what we're able to do today. Also, finances, a huge industry where today there are a lot of assumptions on different financial outcomes. And being able to use quantum computers would let us avoid these wide blind spots of our assumptions, and will enable us to do a lot of optimization of our investments, portfolios, fight fraud detection, etc. And of course, cryptography and other domains are here. So where are we now? As I said, we have some domains where we're going to see some results in 5 to 7 years versus domains that will take more than a decade. And we can only imagine what will happen in a world maybe not very, very far from us, when we're going to have tens of thousands, hundreds of thousands, and maybe a million qubit quantum computer. This will change everything. But we already start to see the flywheel effect. Already we start to see hardware, quantum computers that start to operate. This draws the attention of companies that are designing algorithms, software frameworks, and enable other companies to play with that. This already draws the industry, the people that work on materials, on financials, insurance, pharma companies, to have expert teams in quantum computing. Just last week, Jonathan and I were on a roundtable by an insurance company that was asking us questions about quantum computers, and that's an insurance company. So really, the main industries understand that they cannot leave this domain untouched. They need to be in the play. They need to be in the game. And I would like to end with a very interesting concept. So we talked about Moore's law, where the processors, the number of transistors doubles every 2 years. And Sakhalin, a journalist, found another phenomena that is really, really interested in. On purpose, he called it E-room law, which is Moore's law on the opposite, reverse, right? E-room law. And what E-room law says is that every 9 years, the number of drugs that the FDA is able to approve is halved. And this happened since the 50s. And the reason is that if in maybe 10, 20 years ago, it took us tens of millions or maybe hundreds of millions of dollars to develop a new drug for a disease, today we're in a situation that it takes billions and even more to develop a new drug. And the idea is that in maybe less than 5 years, some of the diseases, it's going to be too expensive to develop a drug for them, because we're not going to see return on investment in their lifetime. Even drugs that already today, people pay for them maybe $50,000 per month. We're not going to be able to return, and and the pharma companies will stop developing drugs for some of the diseases. So this is a very scary situation, and really we need quantum computers to be able to discover new drugs faster and to be able to run the clinical studies much, much faster than what we're doing today to solve this. So this returns us to the penicillin that we talked in the beginning, and I hope we're going to have quantum computers soon. Thank you very much.
Don't do drugs. Our last speaker for this session, and then you're going to have a break with some wines, is Fred De Leo, who made all the way from Netherlands. Fred is an investor in AI, in quantum, in automotive, and in fintech, and he's also a mentor at Startup Bootcamp. Fred, stage is yours.